So in the previous video's lesson, what we looked at was we looked at how to take the Laplace transform, definition of Laplace transform, and then we took a look at the inverse Laplace transform. And now what we're going to do is we're going to look at what we can do with all of those different functions. And the first thing that we're going to learn how to do is we're going to learn how to find the derivatives of Laplace transforms. Now, one thing that we're going to do is we're just going to verify for a very basic case a first derivative of a Laplace transform. So in other words, if we had a derivative of a function or maybe a y prime. What we can do is we can stick that into the very definition of the Laplace transform. Right? And remember, this is our definition. We showed, I think, 3 of those, how that worked. And instead of f at t, we just have f prime at t. And one of the techniques we used a couple times was integration by parts. And so by integration by parts, if u is equal to e to the minus st, then we have minus s e to the minus st dt. And if dv is f prime t dt, then we just go back to the original function. And so what we can do is we can just go through, substitute back in for our uv/vdu right here. And what you'll notice is that this quantity is going to go to 0. If we have f at 0, that's just going to be our initial value, and then we have this e to the minus st. We're just going to assume that that grows bigger than our function, our f at t. And so that's just going to be 0 here, so we just get this minus f0, and then we're just going to factor out the s in this limit, and notice that this is the very definition of the Laplace transform, and what that turns into is s times Laplace f at t, or Laplace of the y value, minus f0. Now if we wanted to do this, we could prove this a few more times by subsequent parts, and we can figure out how to take the Laplace of the second derivative, Laplace of the third derivative. And what you'll notice is that there's a pattern. Each time, what you're going to end up with is whatever the order is of the differential, so second order, second s, or s to the second power, third derivative, then the order of the polynomial s is going to be 3, Laplace transform, and then you just go in descending order of s squared times f naught, and then f prime at 0, and then f double prime at 0, etc. And so there's a pattern. And we could prove this by mathematical induction if we chose to, but we're just going to go ahead and assume it. For what we're going to be working with, we're not going to use anything higher than the second derivative to be able to solve using our Laplace transforms. And you might remember that there's a process that we're going to utilize to be able to find the solutions to differential equations using Laplace transforms, as with all integral sorts of problems or integral transforms. So we're going to take the Laplace transform of the original dE. We're going to eliminate the derivatives by using this. And notice the goal is that up here, when we took the Laplace transform of the derivative, there are no derivatives. And that's the goal, is to get rid of all those differentials. Now we're going to have an algebraic equation, so we're just going to go back and we're going to solve for y at s, or Laplace of y, or whatever the original function is. Maybe it might be Laplace of f at t, whatever it might be. And then we're going to find the inverse. All right, and that's the hard part, as we saw in the previous video series. So let's take a look at one rudimentary example of this. Okay, so we have a very basic first order differential. We have y prime minus y equals 1. Y at 0 is equal to 0, and we're going to solve this using only a Laplace transform. Now certainly separation of variables will be a lot easier, but let's just use this to illustrate the process. So when we go through this, we're going to take the Laplace transform of each term. So we have Ly prime minus Ly is going to be equal to the Laplace transform of 1. Now we can go back up, and we can use this rule that the Laplace transform of one derivative, in this case y, is going to be s times the Laplace of the original function, in this case y, minus f at 0. And so this is going to now turn into, so I'm just going to use a different color just to illustrate. So this is going to turn into SL of y minus y at 0 minus, now this is going to just stay L of y, And then finally, we know what the Laplace transform of 1 is. Remember, the Laplace transform of 1, if we look at that table, is 1 over s. All right, pretty neat. Notice that there are no derivatives now in the new equation. It's an algebraic equation. All right? Now, at this point, the goal is to solve for L of y. And to do that, we'll notice that we have an Ly and an Ly, so we could just factor that out. So that's going to be Ly, and we're going to be left with s minus 1. Now, if you don't trust me, what you could do is you can just distribute that back out. And then also this y at 0, well, notice that we said y at 0 is equal to 0. And then finally, on the right-hand side, we still have 1 over s. If we solve for Ly is going to be equal to 1 over s times s minus 1. All right. So now we've solved for Ly. All right. Up here, we took the Laplace. All right. And if we're looking at our steps up here, we took the Laplace, we solved for Ly, and now we need the inverse Laplace. All right, and as we've seen, that's probably the most difficult part. Okay, so now we're going to find our inverse Laplace. And so, now this might get a little bit ugly, but we're going to have inverse Laplace of y is going to be equal to inverse Laplace of 1 over s minus 1. Right? Another way to write this, we know that the inverse of the Laplace, so in other words, if we had an arc sine of a sine, as long as it's within the domain, that's just going to turn into y. So y is going to be equal to the inverse Laplace of 1 over s minus 1. And now we go back to those techniques that we looked at in the last section. How do we find an inverse Laplace? One of the techniques that we used was partial fraction decomposition. So let's decompose this animal right here. So we're going to have 1 over s minus 1. Now notice we have all linear factors. So we have a linear s and we have a linear s minus 1. So the undetermined coefficients for this, or the undetermined variables, whatever you want to call them, are going to be a over s plus b over s minus 1. We're going to multiply through by the common denominator, and this is going to turn into 1 equals a s minus 1 plus b times s. And then what we can do is we can go ahead and collect all of the s terms. So we can rewrite this as 1 equals, we have an as and a bs. If we factor out the s, that's a plus b. And then we have a minus a. And what I'm going to do is, I'm just going to write this as 0s plus 1. And the reason I do that is because now we can go through and we can match up and create a system. And so our system is going to become a plus b is equal to 0, and then negative a is equal to 1. And this is pretty obvious. This means that a is going to be negative 1, and since a is negative 1, we get negative 1 plus b is equal to 0, or that implies that b is going to be equal to 1. And remember up here, we had our a over s plus b over s minus 1. And that was equal to, hopefully, this structure right here. And so what we're hoping is just to take the inverse Laplace of those. Okay, so y is now going to be equal to the inverse Laplace. Remember, we had a over s, so that's going to be negative 1 over s, plus inverse Laplace of b, which is 1 over s minus 1. Right, and we're almost done with this now. So now we end up with y is going to be equal to the opposite of L minus 1, 1 over s. And you could probably just look on the table, or you can use the translation theorem. Remember, we have that first translation theorem, so we can actually rewrite this as L minus 1 of 1 over S as S tends to S minus 1. And in this case, A is going to be equal to 1 in our formula for that first translation. And so what's our final answer, or at least our final guess? Y is going to be equal to, now remember, 1 over S, the Laplace of 1 over S is 1. So, or I'm sorry, the Laplace of 1 is 1 over S. So this is just going to turn into negative 1. Right? And then this is going to turn into 1. But then right here, this is going to be our e to the 1t. Right? And again, that's because of our first translation theorem. Okay. And then finally, we could just rewrite this as 1e, or y equals e to the t minus 1. All right, now, the question is, does this even work? All right, well, let's just check our answer just to make sure, because our differential is really easy. So remember, this was our original differential. Y at 0 was equal to 0. So let's test that out first. That's nice and easy. Y at 0 is going to be e to the 0 minus 1, 1 minus 1, and by multivariable numerical methods, 1 minus 1 is 0. So that's good, because at least that says we've got the right initial value. The derivative, y prime, is e to the t, since our derivative of negative 1 is 0. And so by substitution back into y prime minus y equals 1, y is e to the t. Remember, our solution y was e to the t minus 1 equals 1. Does that work? Well, e to the t minus e to the t is going to be nothing. Opposite of negative 1 is 1, so 1 equals 1. So yeah, this is indeed the solution right here, e to the t minus 1, using our Laplace transform. All right, now, was it easier to use a Laplace transform? Certainly not. It was more difficult to use that. However, what we noticed is that it was a method that works, and it's not a series method, although we could use a series if we really wanted to. So hopefully this gives you a good overview as to the process of the derivatives of Laplace transforms, as well as finding the solutions to differentials using Laplace transforms. In the next videos, we're going to take a look at a few more examples of this.